In the last couple of lectures, we've talked about ways to get instruction level parallelism between code that has a lot of branches. Now we want to talk about a way to get thread level parallelism in a similar situation. The kind of data structures we're going to be talking about today are linked data structures, and the problem is that they tend to be accessed in loops, and those loops are inherently sequential, so how do we get some parallelism? First of all, let's take a look at what kind of linked data structures we're going to be talking about. Linked lists, certainly, but also trees and hash tables and just in general graphs. These are all data structures that have some links to them. In the case of a graph, the links can be in no particular order, just between various nodes. But yet, if you want to operate on them, you've got to do so in a loop, and it's going to be difficult to do that because you need to get one pointer and then find another pointer, etc., sequentially. So let's take a look at a piece of code that illustrates such a dependence. And this is a method that tests for a particular key value. And if a key value is found in the list, then an integer x is added to the data portion of that cell. So what we're going to be doing is walking through the list and looking for a key that's equivalent to a key in a node, that is, that's the same as a key we passed in. And if we find one, then we're going to be adding x to the data field of that node. And then, of course, we need to set p equal to p points to next to get ourselves back around into the next iteration of the loop. Now, we don't have an I for an iteration number in this code, but if we did, we could write the dependence s2 of I has a true dependence with s2 of I plus 1, which means that you can't calculate where you're going to be after the next iteration until you know where you're going to be after this iteration. Well, if we look at the loops of a linked data structure here called LDS program, we won't find any parallelism to be exploited because the links, the nodes are all sequential in nature. Or that is to say, the links, the lists are all sequential in nature. Now, back when we looked at Guy Steele's lecture on data parallel algorithms, we did see that it was possible to get some parallelism traversing a loop, but that's only if you had each of the threads beginning at a different point in that loop. And here we have a single thread that begins at the beginning of the loop, so there's no easy way to parallelize it. So when can we find the opportunity to execute anything in parallel? Well, I guess we'll have to look at the algorithm level, which is to say we want to run these operations, run these loops with function parallelism. So you have different threads that are, for example, searching for a value in a loop while another thread is trying to insert something in the loop or delete something in the loop. Conceptually, we can allow several operations to be performed in parallel. Now, I've just talked about a couple of kinds of operations, and you might think for the next second or two of other kinds of operations that we might be able to run in parallel. I think I mentioned search and insertion, but it's also possible to do a deletion in parallel with an insertion or a deletion in parallel with a search. But not always. How do we decide which operations can be performed in parallel? Well, in order to do that, we've got to figure out what goes on when we have these various operations, insertion, deletion, search, etc., going on at the same time in a list. And that'll be the subject of our next couple of videos.